The Fabry-Perot interferometer is formed from two mirrors. They have coatings on them which transmit some light and reflect most light. Light incident from the left impinges on the first mirror. Light gets into the space between the mirrors and becomes trapped as it reflects back and forth. The reflecting light interferes with itself, forming some sort of interference pattern, which we're going to go over in this video. These two mirrors form an optical resonator. Their spacing determines which wavelength of light will resonate between them, giving bright light at the output side. If it's a Fabry-Perot echelon, these two mirrors are not movable relative to each other. They're fixed in place. When they can be moved relative to each other, then it's referred to as an interferometer because then it's useful for measurement applications. But when you have two reflecting surfaces just facing each other, you can get resonances that you can't control by moving the mirrors, and it's often an unwelcome property of a system, and it's often referred to as Fabry-Perot modes. You'll hear this term both in optics and in microwaves to refer to resonances that occur when you have two counterfacing reflecting surfaces. Two responses of the system to light are to reflect it and to transmit it. Voltage transmission coefficient T tells you how much of the electric field makes it through one mirror, and the voltage reflection coefficient R tells you how much of the electric field reflects off of each mirror. The incident beam has an amplitude of E0. That's the amplitude of the electric field in that wave. It passes through the first mirror with a transmission coefficient T, which means some of that electric field reflects off the coefficient of R. It obeys the law of reflection, so the angle of reflection is also theta. It transmits into the space between the mirrors and strikes the opposite mirror. Some of it transmits through that mirror, again with a transmission coefficient T. And so the electric field that comes out of the mirror is the incident electric field E0 times the transmission coefficient T squared. Some of that light reflects back from the second mirror with the coefficient R, and then it strikes the first mirror, and some of that light passes through with another transmission coefficient T, and some of it reflects off with another coefficient R. And then some of that light passes through the second mirror with another transmission coefficient T. So you can see how these powers of T and R build up as light bounces back and forth, some of it leaking out the second mirror, some of it leaking out the first mirror, and is lost, because we're going to put our eyeball at the second mirror and look at the light coming out. And it just goes on and on. The light that comes in can be divided up into little rays, and we can do this analysis on them and add up all the light that comes out. But as each successive ray leaves the interferometer, it's going to have a different phase than the previous ray because of the added path length. First ray that comes out has phase 0, and so all other rays have their phase measured relative to it. Phase delta, we'll call it, and we'll say the next one is 2 delta and 3 delta. So we'll multiply a factor of e to the I delta to all of them to account for the phase shift of the extra path length. And then add up all of these wave amplitudes to get the output wave, and that's what the eyeball sees. That's a big, long, infinite series expression down there. Let's take our infinite series of electric field amplitude terms and factor out what's common, and what's common is E0 and T squared. And recognize that each one of these terms is R squared e to the I delta raised to a power, 2, then 3. And now replace R squared e to the I delta just with X. You might immediately recognize this as a geometric series. The expansion of these terms with x less than 1 is 1 divided by 1 minus x. There's a caveat that x is less than 1, but that's not a problem because r is a fraction of reflected electric field. Putting this into that form and replacing x with r squared e to the I delta gives an expression for the electric field amplitude that is transmitted through the two-mirror system in terms of the transmission and reflection coefficients and the phase shift delta, which is associated with the additional path length that each reflection undergoes. We need to find an expression for delta, and we're going to do that next. Just as a little hint, it's that gray expression right there. This expression in the box describes interference of the waves coming out of the two-mirror system. What it doesn't do is it doesn't convey how fringes occur. And you know, one of the objectives of a Fabry-Perot experiment is to look at the fringes. So far, we haven't done anything that shows that fringes occur. In order to do that, we need to look at what this expression tells us. beginning with the phase shift delta, which is a consequence of this extra optical path length that each ray has relative to the next ray. And that extra optical path length is this purple curve. In the setup, light is coming into the interferometer at an angle theta, and so these rays 1, 2, 3 up to a lot are all parallel to each other. Ray 1 enters the interferometer, it reflects off the back mirror, comes back to the front mirror, and it joins ray 2, and they head out together. But ray 1 has been shifted in phase and is therefore interfering with ray 2. Inspection will quickly lead to the conclusion that these lengths are just d over cos theta in one case and d over cos theta times cos 2 theta in the other case. Add them together to get the difference in optical path length between rays 1 and 2. Do a little bit of trigonometric manipulation, and the difference in optical path length between ray 1 and 2 is simply 2d cos theta. That's the same difference in optical path length between ray 2 and ray 3, and between ray 3 and ray 4. Divided by the wavelength, that's the fractional shift in phase. Multiply that by 2 pi, and you have the actual phase shift that the ray undergoes as it proceeds from the beginning of the purple region to where it rejoins ray 2. That's not all of it, though. There's an additional phase shift. Every time a wave reflects off of a metallic surface, there's a phase shift, and it is significant. I'm going to call that shift in phase, that metallic reflection, phi over 2. When ray 1 rejoins ray 2, it's reflected twice. It has shifted a phase amount phi. And this phase shift, due to reflection off of the surface, is always ignored. Not just usually ignored, but really always ignored. But why? Is it okay to do that? We're going to answer that at the end of this video. After we get a result, then we'll introduce that phase shift and see what difference it makes. Let's also clear up the meaning of these voltage transmission and reflection coefficients. R is the voltage reflection coefficient, and square it, you have the power reflection coefficient. So R squared is the ratio of power reflected over the incident power, and for transmission, big T is the power transmission coefficient. It's a ratio of transmitted to incident power, and it's the ratio of indices on either side of the interface times the ratio of the refraction angles. In most uses of a Fabry-Perot interferometer, the angle of incidence is nearly or exactly normal, so setting these angles to 0 results in a simplified transmission coefficient of just the ratio of the indices. When the ray starts on the left and ends on the right, it has gone through the glass twice. Altogether, the transmission coefficient for power squared is little t to the fourth. This script E is the electric field, and I'm using that symbol for electric field instead of capital E because capital E is being reserved for irradiance, the watts per square meter on a surface. Some would call it the intensity. We should really call it the irradiance. Irradiance is proportional to the electric field in the wave squared, and so I'm going to write the irradiance as some amplitude of irradiance times that expression for electric field squared. T to the fourth I replace with t squared, t being the power transmission coefficient, and now replace the little r squared with big R, the power reflection coefficient. The I delta is complex, and the denominator is the modulus of that complex number. You can take a modulus by multiplying a number by its complex conjugate, and that's the mod squared of the denominator. Using this trig identity as well as the Euler relation, I can then rewrite the transmitted irradiance E sub t in terms of delta, that phase shift, without any complex exponential. And that's our working expression for the transmitted irradiance coming out of the two-mirror system. In the event that delta over 2 is an integer multiple of pi, then the denominator in the big parentheses is just 1, and the entire expression is a maximum. So this ratio up front, E0t squared over 1 minus r squared, is the maximum irradiance as you vary the phase shift delta. This ratio of r and 1 minus r has been replaced with big F, called the coefficient of finesse. I'm going to go through what that means momentarily. I want to make a graph of it, and so I put together this little MATLAB code to do that. You can pause the video and take a look at it. The transmitted irradiance, normalized to its maximum, as you vary the separation between mirrors, is periodic. One of the variables is big R, the reflection coefficient. So we have 3 different graphs here for 3 different values of big R. Put it in terms of 3 different values of finesse. If the reflection coefficient is very large, these peaks are very sharp. And so finesse sort of makes sense as the term here, because if the finesse is large, like 80, you have sharp peaks. That is, you have to be at the exact mirror separation in order for light to come out the other side. There are two different expressions that you see for the finesse. One is the f that I introduced previously based on the reflection coefficients, which is usually called the coefficient of finesse. If you take the square root of the coefficient of finesse, then multiply by pi over 2, you have the finesse, which is a useful parameter because it's exactly equal to the spacing of these peaks divided by the width of these peaks. Another way of looking at this is to divide the mirror separation by the wavelength. Now I did this calculation with a wavelength of 1.2 microns, just arbitrarily selected. The function looks the same because all I did was divide out a constant, the wavelength. Then you realize that the separation between these peaks is half a wavelength. So if you change the separation between mirrors, every time they change by half a wavelength, you go through another peak in the light that is transmitted out the back. If you have a high finesse, then in between these two peaks, you have virtually no light getting out. That's contrast, when you can distinguish between being on a resonance and between two resonances. So high finesse corresponds to high contrast. I'm going to use simulation with Zemax Optics Studio in order to explore certain parameter space that's not easily controlled in a hard experiment. But in a soft experiment, we have a lot more buttons. I want to look at the irradiance at the back side of the mirrors as I adjust the separation between the mirrors. I expect from the equation that we derived that as the gap between the two mirrors gets larger, it will periodically pass through nulls and maxes as delta cycles through 2 pi over and over again. What I get from the soft experiment is in fact that happening. I did the experiment at a wavelength of 1.2 microns, and I found that every 0.6 microns, or half of that, is a maximum in the irradiance emerging from the system. And in between, it doesn't go to 0, but it does become a minimum. What does the graph of the equation look like for a 1.2 micron wavelength? It looks exactly the same, almost. And every 0.6 microns, there will be a peak. As the mirror spacing continues to grow, you see is more and more and more of these peaks. I'm only narrowing in on 2 of them. And the same happens in simulation and in the theory. What's different is that the peaks appear to be wider in the simulation. And the calculation was done with a reflection coefficient on the mirrors of 50%, as was the simulation. So why are the peaks wider in the simulation? Which one's right? Well, equations are less realistic than simulation, and simulation isn't exactly the same as experiment. Although in simulation, you can control the parameters so you know what's causing the outcome. And I know that the outcome on the left from the simulation is different from the outcome on the right from the ideal equations because the simulation accounts for additional reflection off of the uncoated glass surfaces of the mirrors. If I remove the reflection off of those back surfaces, then I get exactly what the equations show. So it's these back surfaces that don't have coating. The light reflects off of both of them as well as off of the metallized mirror surfaces. So I eliminated that reflection simply by setting the index of refraction of the glasses to 1, and the response looks just like the equations. If the mirror spacing is held constant and the wavelength of the laser is adjusted, which is experimentally a very difficult thing to accomplish, there will also be peaks that are separated by what's called the free spectral range. And for that, you can watch my separate video on the free spectral range of a Fabry-Perot Interferometer. The graph of the working equation versus wavelength now, keeping the separation constant, here I kept it at 100.16 microns, gives peaks that go on and on and on as you keep changing the wavelength. Or if you look at it in frequency domain, which is simply a matter of flipping the wavelength over and throwing in the factor of the speed of light, you also have repeated peaks. Now in frequency domain, these peaks are exactly the same separation forever. In wavelength domain, if I look over a long enough range of wavelengths, I'll see that the peaks get closer and closer together. The free spectral range, or the separation and frequency domain of these peaks, is c divided by twice the spacing. And so if I wanted to actually calculate what a resonant frequency would be given another one, frequency of one mode minus the frequency of the one just before it is c over 2d. Or in wavelength language, replacing the f with c over lambda, I can say 1 over the wavelength is 1 divided by twice the separation. So as an example, we use 100.35 microns, and with that, we find that there is a resonance at 1.202 microns using the big equation. Now, given these two facts, that we have this separation and we have a resonance at this wavelength, we can calculate all the other wavelengths where there is a peak. And let's look at that in simulations. Now, this was very tedious, so that's why there are very few data points, but sweeping through several wavelengths and measuring the irradiance, I find that wherever these resonances are predicted, there is in fact a resonance. But now all we're doing here is looking at the irradiance coming out of the back mirror. There's no pattern to it. In fact, I used a single pixel detector to pick up that radiance in the simulation. There are in fact fringes, they just don't happen automatically. There are two ways to see these interference fringes. The first method is to tilt one of those mirrors. So if one of the mirrors is at an angle, then consequently as you move along the mirror, delta is slowly increasing. Every time the light traverses the cavity once, it's with a slightly bigger delta. And so then you have an oscillating electric field coming out of the mirrors. And that oscillating electric field then shows up as a series of dark and bright interference lines. That gives you these Fizeau patterns, these parallel fringes. A second way to see interference fringes is to ensure that the beam is not collimated. That way, every piece of the beam is striking the mirror at a slightly different angle. And again, you have this spatially dependent delta. Increases radially as you move out from the center. A series of radial interference fringes, or circular interference fringes. And that's the famous bullseye pattern. And for that, you can watch my video on getting a bullseye pattern with a microcosine interferometer. It's very difficult to have perfectly oriented mirrors, and you always have a non-ideally collimated laser beam, so you would in fact have a mixture of these two patterns. The challenge then is to align those mirrors well so that you don't have parallel fringes. I'll give you a brief summary of how I set up the simulation in Optics Studio. This is the three-dimensional view. The orange part is the lens, which is weakly diverging, and then there are the two glasses, which are metallized on the interior surfaces facing each other. Light comes in from the left and passes through the lens, diverges slightly, and hits the interferometer, and then comes out of the interferometer and arrives at the detector. You may just want to put the detector right on the back surface of the interferometer, since that's where you look when you do the experiment. Setting this up in the component editor, I chose a simple elliptical source. I gave it 200,000 analysis rays and only 100 visible rays, and I made it 6 millimeter diameter in the X and the Y direction. And then there's the lens. I gave it a curvature of minus 1700 millimeters. For the material, I could put in a real glass, but I didn't want to deal with dispersion. I'm doing this monochromatically anyway, so I just gave it a 1.52 index. And if I want to do an experiment without a collimated beam, I just set the index to 1. I made the mirrors with standard lenses as well. I set their curvatures to 0. Optics Studio interprets that as infinity. I could likewise just make that a very large number. The key thing with these two items, items 3 and 4, double click on one of them. When you go into coat scatter, you have to indicate a coating backface. That's important. Now I put a 50-50 backspace on there, so it's coated as if it were a 50-50 splitter. There are several coatings you could choose. Sometimes I use this thin aluminum coating, which I found somewhere and uploaded, but it's very similar to a 50-50. Object 3 has a coating on the front face, so the coated sides of the mirrors are facing each other. Null object actually isn't unnecessary, except to position the detector somewhere other than right at the end of the second mirror. And the detector type is rectangle. It's an 8mm by 8mm square. I gave it 100 pixels, but in that first experiment I showed you, I used 1 pixel because I wanted to get the irradiance coming out of the mirror. It'll look something like that depending on conditions. Instead of having bullseye fringes, if I wanted parallel fringes, set the index to 1, put a little bit of tilt on the second mirror. 0.025 degrees is what I've been using. And look at it, and we have parallel fringes. For the first experiment, let's make that lens weakly diverging so that we have an uncollimated beam and a bullseye interference pattern appears. Let's vary the separation between the mirrors with that condition, beginning at a separation of 100 microns, which by the way is arbitrary. It could just as well be 1 millimeter. Start to increase the spacing. You see the bullseye closing in on itself. The question is, by how much do I have to change the mirror spacing to get the fringes to move by one fringe? The way to determine the fringes moving by one fringe is to find two positions where the pattern's identical. At a spacing of 100 microns and a spacing of 100.6 microns, you see really identical bullseye fringe pattern. It took 0.6 microns to get one fringe to pass by. That's half a wavelength. And that's the idea, that when you have displaced the mirrors by half a wavelength, you get one fringe. And that's exactly what happens here. In the second experiment, we'll remove the diverging power of that lens so that we have a perfectly collimated beam, but tilt one of the mirrors 0.025 degrees, producing these parallel fringes. Once again, let's vary the separation of the mirrors. And starting at 100 microns again, increase the mirror separation. When we're at 100 microns and we're at 100.6 microns, the fringes are at the exact same position. So one fringe passes by as the mirror is displaced by 0.6 microns. So in the first experiment, the beam was diverged slightly, and in the second experiment, one of the mirrors was tilted. It turns out it doesn't matter how much you diverge the beam, and it doesn't really matter how much you tilt the mirror. The more you tilt the mirror, the closer together these fringes will be, but you'll still have one fringe passing by when the mirror separation changes by half a wavelength. And when you diverge more strongly, you'll get a bullseye with more circles in it, but half a wavelength displacement causes one fringe to pass by. Now, as an appendix, I had raised this question: what is the consequence of ignoring the phase shift that occurs every time the light reflects off of the metallized mirrors? When the light beam strikes the metallized mirror, it undergoes a phase shift, which I'm calling phi over 2. And that has to be included in addition to the delta phase shift that occurs from the light traversing this optical path length difference. Every time the light reflects off the surface, there's an additional phase shift of phi. So we'll add e to the I phi for the first one, e to the 2i phi for the second one, and so on. So the electric field in the wave emerging from the interferometer has to have this extra phi added to the delta. It's only a phase shift. Propagate that through the calculation of irradiance, you realize that's it, that the reflection off of the metal surface simply shifts the phase of this sine squared in the denominator. Let's throw some real numbers in here. So if that metallization were gold, for example, because I can find a number for it, gold is a complex index of refraction shown here. Okay, it's at 530 nanometers, but that's not really the point. Let's go ahead and calculate the reflection coefficient, and it's a complex refractive index, so the reflection coefficient itself is complex, which means that it has a phase. Let's get that phase, and the phase is minus 0.71 radians. Go ahead and insert that into the expression for irradiance, where there's phi, and make another plot in MATLAB. Now, this was the original plot that we had. Adding the minus 0.71 radians, you get that. So the consequence of ignoring that phase shift at the mirrors is that the actual mirror separation where you have resonances is slightly modified. That is actually the least important detail in analyzing a Fabry-Perot interferometer. It's all about changes. How many fringes pass by when you make a change. But the change matters. So it's really not important that this phase shift on reflection is ignored. That was everything that I had to tell you today about the Fabry-Perot interferometer. Now, hopefully you're prepared to do an experiment with it.